Now we're going to look at how to combine capacitors in a circuit. So it's going to be similar to resistors. Similar tricks to resistors, but look at charge. Resistors we used V equals IR to figure things out. Here we're going to use Q equals CV. So let's make this circuit first. Up here, let's put in a switch just to keep things spicy here. And then it comes down very similar to the last circuit. Let's put two capacitors there, one capacitor there, another capacitor there. And let's give them all the same capacitance C, 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 C. And ask the question, if the battery has EMF, E, is how much charge flows when you close the circuit? How much charge from the battery when closed? I'm running out of room here. Okay, so sort of a before-after thing here. So before the switch is opened, it might be obvious to you that no charge flows, or maybe not. You could say, well, the charge might flow here. So what we're going to do to make this kind of exciting is we're going to treat the switch as a capacitor. We could have done it with the resistors, actually. Open switch, infinite resistance. Closed switch, zero resistance. But here I'm going to show you we can actually take the value of the thing of interest, right now the capacitance, just put the switch in as though it's an element, and then we'll really know exactly what will happen when we open or close the switch. So let's do switch open. All right, and the approach is you say the battery doesn't know anything. For the battery, the total charge it sends out is the equivalent resistance, the equivalent capacitance times the EMF. So we're trying to find the equivalent capacitance of the whole thing. What does it see? All right, so the equivalent capacitance, it looks like we have this in series with this, in series with this, in series with this. So the way you add capacitors in series is unfortunately this whole inverted thing. So capacitance of that. What is the capacitance of an open switch? It is really small. It's like zero. Because think of a capacitor gets a big capacitance when you have two big plates close together and a lot of area to hold charge. This is just this little wire and this wire. They don't have a lot of area to hold charge. So it's not zero. I mean, a little charge might sit here and here, but it's essentially in the ideal limit of a switch, we'll call it zero. All right, another one in series, 1 over C. And then this big mess in series, so 1 over this big mess. But what is this mess? This mess is this in parallel with this. So capacitors in parallel add, so that's nice. So C plus, but then choose series again. The inverse of 1 over C plus 1 over C. So just to save us a little bit of time, I'll tell you that two identical capacitors in series, when you do the whole inverted formula, you get a half C. So I'll say C plus 1/2 C. So there's the branch plus another 1 over C. Okay, so we could go on, but what we can see here is when we play with infinities, say this will be some number, this will be infinity. So infinity plus a number is still infinity. So 1 over the equivalent capacitance, 1 over it is infinity, so the equivalent capacitance is 0 in this case. So the open switch indeed does not allow any charge to flow. We can even confirm that mathematically. Now let's close the switch. One over the equivalent capacitance. Equivalent capacitance is 1 over the switch. What is the capacitance of a closed switch? this is the tricky one, it's infinity. How can it have infinite capacitance when it's a closed switch? When it's a closed switch, it's a wire. How can it have infinite capacitance? It's because what a capacitor does is, it's a question of how much charge do you, or how much voltage do you have to apply to get some charge. Well, you're never going to build up charge in a wire. You could apply infinite voltage and you would never build up any charge, which means it's like a capacitor where you can just send charge forever and nothing happens because it's infinitely big. So a closed wire, closed switch, infinite capacitance. And you can see that's going to have it not screw up our circuit, so it's also, or our equations, that's also useful because that's 0. 1 over C plus 1 over C plus a half C, the rest is all the same, plus 1 over C. So now with the switch closed, the equivalent capacitance won't be 0 because that term is now 0. And we just have to add up the other 3. No, I see. So it's different from my notes. I drew a different. Sorry, I drew a different formula. Actually, no, we're all on here, so I can cough one more. Let's see. So let's go ahead and just sort of add this. Running out of room here. So 2 halves plus 1 half is 3 halves C. All right, which makes this 2 over 3C. All right. So we go for a common denominator of 3 over 3C. Yes, and we get that 1 over C EQ is what? 368 over 3C. So the equivalent capacitance is 3/8 C. Yes, and it makes sense that it's going to be lower than C. Resistors, you put them in series, you get more resistance. Capacitors, you put them in series, you get less capacitance because they're having to divide up the voltage drop that's applied. Okay, so there's your equivalent capacitance of the entire circuit. What was the question? How much charge from the battery would close? Okay, so it went from equivalent of 0 to equivalent of 3/8 C. Now we actually have to say how much charge is going to flow. Well, we go to this. Charge is going to be that equivalent times EMF. So the Q initial is 0 because the capacitance is 0, 0 times E. And then here it's 3/8 CE. Q final is 3/8 C times the EMF. So that's how much charge flows from 0 to 3/8 times the capacitance times the EMF.